All right, this video is for calculus, the last video in the series on vectors, and we're going to talk today about velocity and acceleration as vectors. So earlier in the course, we defined motion in one direction only and said that if you have a function that represents distance, or sometimes called displacement versus time, then the derivative of that is the velocity, and the second derivative is the acceleration. So the derivative of distance is velocity, the derivative of velocity is acceleration. And that would allow only motion in one direction. So we could define a direction like this to be positive on this side, negative on this side. Maybe distance would be given by some equation like this, and the units would be maybe meters, right? We could take the derivative of that, and that would be the derivative of that would be, we call that velocity. Could give me an equation for that. The units for that would be meters per second, and then the derivative of that, the derivative of the velocity would be acceleration, and the units for that is meters per second, or meters per second squared. And then if we wanted to find the average velocity, that would mean that you just take the displacement between two different locations divided by the time, and that would give you the average speed, whereas the derivative gives you the instantaneous speed, right? But all this stuff was only in a single direction. So to analyze motion in 2D, two dimensions, we can represent the position on the 2D plane as a vector valued function. So t will represent time now specifically, and we'll have the x and y components of the object, and it's not restricted to be a function. It can move anywhere because we're using like a parametric version, right? So the position vector will point to the x and y coordinates of the position, and those are functions of time, so we can allow those to trace out any path. If we take the derivative of that, that will give us the velocity. And then the speed, that is defined as the magnitude of the velocity vector, right? But with a vector, we now know not only the speed, right, how fast the object's moving, but we know the exact direction at every point in time. So we can plug in a particular time, find the direction and speed at every location on the path, which is really, really powerful. All right, and then if we take the derivative again, we get acceleration. So that's the second derivative of position. The first derivative of velocity gives you acceleration, and that is a function of time. Okay, but that is related to the concavity. So it is kind of related to the curvature, but with a position function, what causes an object in motion to deviate from its course is a force. Newton's second law of motion is F equals ma, which means the acceleration is just the force divided by the mass. So if we have the acceleration as a vector, it means the force that causes that acceleration can now be a vector. So I just think of it as the acceleration is, if you're pushing on something in some direction, the mass is the property of the matter which resists changing direction. So if you have a small mass, a particular force will cause a large acceleration, and if you have a large mass, a particular force will cause a smaller acceleration, right? But the force and the acceleration are in the same direction. So that means if you take a position vector, this r, and you take its derivative and you find the velocity vector at any point in time t, and you take the derivative of that to get acceleration, then if I am at some specific point here where the velocity is moving like here, the acceleration vector is pointing in the direction of the current force that's acting on the object, right? So if there's a force acting in the object this way causing the acceleration, that's going to cause this velocity to bend around here, which is why it's also kind of related to concavity, because it's curving the path, right? But it's in the direction around which the path is curving because the force is pulling the object in that direction, right? Kind of an interesting thing. And then what that also means is it explains something that we haven't been able to explain so far. We know that if you have forces, they need to cause accelerations. But what if you had like a ball on a string and you were spinning it at a constant speed, right? There's a force acting from the string on the object, but the speed is not changing. So how can there be force equals acceleration, causing acceleration, if the speed isn't changing? Well, if you define the force as a vector and you define the acceleration as a vector, the magnitude of the acceleration doesn't have to change, but the direction is changing, right? So that force is causing a change in the acceleration vector's direction, even though the velocity is staying constant. Right? So in physics, forces always cause accelerations, but they don't necessarily cause changes in speed. What might be changing from the force is simply the direction that the object is moving, like in the case of orbits, right, for planets. All right, so if we have a position vector, we can take the derivative of that and get a velocity vector. And if we have a velocity vector, we can take the derivative of that and get an acceleration vector. And we can go the other direction. If we're given the acceleration, which we often are because those things are caused by forces, then we can take the integral of that to find the velocity vector and the integral again to find the position vector. So we're going to do a couple of examples here so we can see how this works. First, let's take this case here, where we're given the position vector and we want to go with derivatives to get velocity and acceleration. This is the easier case. So if we have that, the velocity vector would simply be the derivative of the position vector, r prime. So we'll take the derivative of this. So this would be 3t squared. Derivative of cosine is negative sine, so minus 2 sine t. That's the x component. And the y component, the derivative of the sine is cosine of t minus 2t. So we can take a position vector and easily turn it into a velocity vector. Okay, and then I can now find the acceleration vector. That is simply going to be the derivative of the velocity vector, which is the second derivative of the position vector. So I take the derivative again, and I get 6t minus 2 cosine t for the x component of the acceleration. And the derivative of cosine is negative sine t and then minus 2. So easy to go from position to velocity to acceleration. Just take derivatives. Okay? Okay, it's a little more work to go the other direction. If you're given an acceleration and you want to go to velocity and to position, then you have to have some additional information to fix up the integration constants. So if we wanted to go from integration to velocity, the velocity vector is going to be the integral of the acceleration vector. So that means that we're going to take the antiderivative of t, which is 1/2 t squared, and I'm going to put an integration constant. And the antiderivative of negative 10 is negative 10t plus an integration constant. Okay. And then to establish the integration constant, I have to have a known velocity vector at a known time. So if this velocity vector has to be 5, 2, when the time is 2, that means I can plug in a 2 here, plus c, negative 10 times 2 plus d. And that means that the x component here has to match that. So let's see, this is 2 squared is 4 divided by 2 is 2 plus c. So 2 plus c has to equal the x component 5. And therefore c has to be 3. And then this has to match that. So negative 2 times 10 is negative 20 plus d must match 2. So that means d has to be negative 22, right? Yes. No, wait a second. Positive 22, right? Yes, positive 22. Positive 22. All right. So then I can rewrite this velocity vector. Velocity vector with the constants filled in is negative 1/2 t squared plus the constant is 3 for c, and then negative 10t, and then I have to put 22 in. All right, so here is the velocity vector with its constants established. And to establish constants, you have to have a known velocity vector at a known time. Okay, to go to the position vector, we'll take the integral one more time. So RT here is the antiderivative of what we just got. So that's going to be, if I go up to 3 here, 1/6 t cubed plus 3t plus an integration constant. I'll call it c. Maybe I'll call it e. And then the antiderivative here is going to be negative 5t squared plus 22t plus f. All right, and then to establish these constants, we have to have a known velocity vector at a known time, which I do. So the velocity vector has to be 3, 4 when the time is 1. So that's going to be 1/6 times 1 cubed plus 3 times 1 plus e. And then this is negative 5 times 1 squared plus 22 times 1 plus f. So that means that, let's see, 1/6 plus 3 plus e has to be 3. So e has to be, if I subtract a 3 from both sides and move this over, negative 1/6. If I did that right, yep. And then let's see, this has to match this also. So negative 5 plus 22 plus f has to equal 4. So that is, let's see, if I add this over, that's 9. So 22 plus f has to be 9. So f has to be 9 minus 22, which turns out to be negative 13. Is that right? Yeah, 9. Yes, negative 13. Okay, so now that I've got that, I can write my position vector complete with constants filled in. It is 1/6 t cubed plus 3t plus the e constant, which turned out to be negative 1. This is 3t minus 1/6. And then the y component is negative 5t squared plus 22t plus f, which is negative 13, so minus 13. So now I have all my vectors. The acceleration vector was given, but now I have a velocity and a position. I can answer all kinds of questions. This problem just says, okay, let's figure out what the position of the object is at 3. Okay, so now that I have a position vector, I can simply plug 3 in for the time. 3 cubed plus 3 times 3 minus 1/6 for the x component. Negative 5 times 3 squared plus 22 times 3 minus 13 for the y component. And that actually ends up becoming 40/3 for the x component and positive 8 for the y component. So we can locate exactly where the object is at time t equals 3. All right. All right. Next thing we have to cover is, so velocity and distance are related. We know that if you take the integral of the velocity, you get a change in distance, right? Because that's the derivative, kind of the SPAM, start press accumulation method or net change theorem idea. But there's something to be pointed out here. If you kind of use the fundamental theorem and say, remember, if this is a derivative of something, so if this is a derivative of position, then taking a definite integral from some starting to ending time gives you the difference, the accumulation in position here. So, right, the area under a velocity curve gives you the amount of distance traveled. Right, that is called the displacement. It's the total. It's really literally the position at the end of the interval minus the position at the start of the interval. In this case, the position vector at the end minus the position at the start. If instead you need to find the total distance traveled, then you have to do you have to sum up the speeds, and that's because that's an arc length, right? So the basic idea here is, let's say that you have an XY plane, and you've got some sort of pathway along that like this, right? If you just take the definite integral of the velocity vector and plug in the two values, you're going to get a difference between two vectors, which is going to be a vector. So that's going to be like a displacement. It's going to be the difference between the start and the end position, right? But if instead you want to know the distance traveled along the path, that's an arc length, right? And so you're essentially using the arc length formula, the integral from a to b of the square root of the x derivative squared plus the y derivative squared. It's the parametric form arc length equation, although this is also the magnitude of the velocity vector. So you can also think of that arc length as summing up all the little magnitudes of the velocity vectors. All right, so let's do a specific example here. It says here, we're given an acceleration. We want to find the velocity vector, the position vector, the position at 2, and also the total distance traveled from t equals 0 to 2. Okay, so we'll start by finding the velocity vector by undoing that derivative. So the velocity vector here, it's a v, would be the antiderivative of the acceleration vector. So that's going to be, let's see, the antiderivative of 2 is 2t plus a constant. The antiderivative there is t squared plus a constant. We want to fix up the constants if possible with the known velocity vectors. So velocity vector is 3, 5. It's a 5 whenever the time is 1. So 2 times 1 plus c, 1 squared plus d, means that 2 plus c has to equal 3. 2 plus 3 must 2 plus c. 2 plus c has to equal 3. So therefore c has to equal 1. And also 1 plus d has to equal 5. This must equal that. So that means that the d has to equal 4. So we could rewrite our velocity vector with the constants filled in, 2t plus a c of 1, and then t squared plus a d of 4. So now we have a velocity vector. Now we can take the antiderivative to get to position. Position vector is the antiderivative of the velocity vector, which means we do the antiderivative of each term. So that is t squared plus t plus an integration constant. Let's call it e. And then the antiderivative here is 1/3 t cubed plus 4t plus an integration constant, which we'll call f. And then we'll use this position vector to fix up the constant. The position must be 2, 6 when the time is 1. 1 squared plus 1 plus e. 1/3 times 1 cubed plus 4 times 1 plus f, which means this has to equal this. So 1 plus 1 is 2 plus e, must be 2, which means e is 0. And this 1/3 plus 4 plus f has to equal 6. So if I subtract that over, it's 1/3 plus f has to equal 2. So f is 2 plus 1/3, which would be 6/3 plus 1/3 is 7/3 if we did that right. Looks like I got 5/3. So let me see what went wrong there. 4 plus, that's right. It's subtract, sorry, it's subtract 1/3. So it is 5/3, yes, 5/3. Okay, so now that I've got the constants, we can write our position vector, which is t squared plus t plus e, and e is 0. And then y component is 1/3 t cubed plus 4t plus f, which is 5/3. Okay, so now we have the complete motion mapped out. We have the position of the object, the velocity of the object, and the acceleration of the object at all times. So then the further questions they ask here are, what is the position at 2? So for that, we're just going to plug 2 into the position vector. Right, so this is 2 squared plus 2 for the x. This is 1/3 times 2 cubed plus 4 times 2 plus 5/3, which turns out to be, if you boil it all down in a calculator, 6 and 37/3 for the y. So this is a position vector pointing there, or if you want it as a coordinate point, you could write it as 6, 37/3. That's the location. Okay, but since they wrote it as this, I'm going to give it in vector form. Now, this last thing is new. What's the total distance traveled from here to here, right? So I don't want to just plug in 0 into the position vector and 2 into the position vector and take the difference and get the vector pointing there. That's the displacement. The total distance traveled. So the total distance is really the arc length. So we're going to have to use an integral from 0 to 2 of the magnitude of the velocity vector. Right, so the magnitude of the velocity vector is, I'm going to go back up to here, and I'm going to take the square root of the sum of the squares of the components. So 2t plus 1 squared plus t squared plus 4 squared dt. This would be the setup to get that. And if you evaluate that in your calculator, you get 12.281. So that's the length along the path from t equals 0 to t equals 2. All right, that's the last example I'm working, but there's one other example that I've got that I've graphed out just to illustrate the difference between distance traveled and displacement. Here's a different problem. The position vector for this problem is got this x and this y. And if you graph it, it's this red curve right here, okay, from t equals 1 to t equals 5. So we're here at t equals 1, and we're at this location at t equals 5. If you want to find the displacement, what you do is you take the velocity vector as a vector, and you take the antiderivative of that, which gives you a difference in, well, okay, you don't actually do the antiderivative. That would just be the difference in the start and the end. So I'm literally going to plug in 1 and plug in 5 to the position vector and find the two position vectors. So if you plug in 1 to the position vector, this position vector, no derivatives, you end up getting 2.081, 2.841. That's a vector that goes 2.081, let's see, that doesn't really match up with my, no, that's right, 2.081, 2.841. So that's this vector here. This is the vector R1, just to be clear. And if you plug in 5 into the position vector, you get 5.567, negative 2.7. That's this vector, right? So this is R5, right? And the displacement is simply the vector R5 minus R1. So if you take that vector minus this vector, you get 3.486, negative 5.6, which means from here, from the starting position, you're going over the whole trip, you end up being displaced 3.486 to the right and 5.636 down. That's this blue vector here. So that blue vector is the result of doing a displacement calculation. You don't do any antiderivative, you simply plug in the starting and ending values into the positions and take the difference between the two position vectors. On the other hand, if we do the antiderivative of the speed of the magnitude of the velocity vector, that's giving us the arc length. And when you get that, you get 11.465, which is the distance along the path. Okay, so that's the kind of conceptual difference between displacement and total distance traveled. Hopefully that helps you to understand the difference. Okay, that's it for the last video for this portion of the course.